In this video, we're going to learn the process of anti-differentiation, which is just the reverse derivative. And so we call that an integral. So our first vocabulary word is a differential equation. That just means it has a derivative in it. It could be the derivative equal, it could have a derivative somewhere in the middle. And an indefinite integral basically asks for the original function. And so the symbol is going to look like this. And that just says, well, what was that original function? And remember, there are an infinite amount of them. So we did this in class before, but I said, if the derivative is 2x, what was the original? And a lot of people said, well, the original is x squared. Just remember, though, this could have been x squared plus 5 or x squared plus 6 because all of these constants have a derivative of 0. So there's an infinite amount of numbers that could be right there. And so we need to figure out how we can write all of them. And so an indefinite integral and an antiderivative are exactly the same thing. So hopefully that doesn't confuse you. So for our definition, again, we're just kind of looking at the inverse of differentiation. So we're doing the opposite of that power rule for differentiation. Because this constant could be anything, we don't really know what it is, so we put a plus c for constant, and this is called a general solution. A solution is just the antiderivative, so when we integrate, we're finding a solution to a differential equation. And then because we could have any constant out at the end, we do have to put this plus c to represent all of those. So general solution is going to go in this form. We integrate, and then we have to put this plus c. General means what's kind of the general format of every original function. A particular solution is when we find one of those, and we're going to look at that in the next video. In that case, we're going to find that specific c value. In order to do that, we need some point on the line. So for today, we're just going to look at general solutions. So again, this is kind of our notation. This is our integral symbol. We call the function the integrand. This dx is just part of your instructions. So it doesn't do anything other than to identify the variable that's in the problem, but it must be there, and we'll talk more about why that is later. But when this says integrate, we have to know the variable that we're respecting. And we have to make sure that there's only x's in here because this is dx. Okay? When we integrate, we find the antiderivative, and then we have to put plus c. So here are some formulas. Again, they're just reverse of differentiation formulas. So when we take the derivative, any coefficients can just drop down. So when we integrate, if we would rather, we can pull that coefficient in the front because it's just going to drop down as well. When we're adding and subtracting, we can just integrate each piece separately and add or subtract the answers together. And then this talks about that reverse power rule. So again, it's just opposite and in reverse order of when we applied the power rule when we took derivatives. Okay. And then take a minute, pause your video, and write these down. We already know these four. We don't have to memorize anything new. Since we already know these, if I ask you to differentiate, you're going to start here on the left and work your way to the right. So if I said find the derivative of cosine, you know the answer is going to be negative sine. If, however, I ask you to integrate, now we're starting with these guys on the right and we're working backwards to the left. So if I ask you to integrate secant squared, it's saying what's that original function? Well, that original function is tangent. Okay? If I ask you to integrate secant tangent, we know that original function was just secant. If I ask you to integrate something that includes trig, for now, it has to look like one of these on the right. If it doesn't, we need to rewrite it so that it does. Eventually, we're going to learn a method to deal with problems that cannot be written in one of these four types. So for now, we're just trying to make all trig functions look like this. So I've mentioned this before, but when we're integrating, there is no power rule, there is no chain rule, there is no product, and there is no quotient. So if we can rewrite it, we do need to rewrite it. In this case, we have a quotient. So this guy is going to have to be brought up to the numerator. When it does, its exponent becomes negative, and from there we can integrate. Okay? The next one, it's written as a radical. So again, it needs to be written as a power. So we're going to write it as x to the 1/2 power. And then finally out here, if you have a coefficient, you can bring it out front because it's just going to drop down. That does not work if there's any type of addition in here. But if it's a coefficient, it can come out into the front, but it doesn't have to. So now these guys just ask, what was that original function? And so our reverse power rule, again, is opposite and in reverse order of taking a derivative. So we're going to start by adding 1 to this exponent. So when I add 1, I get -2. And then I take this original coefficient and divide by this new exponent. So I get 1 divided by -2. And then we always have that plus c because we don't know what constant was out there to the right. We're going to do the same thing if our exponent is rational. We're still going to add 1. So when I add 1, I'll get 3/2. And then we're taking this coefficient, which is 1, and we're dividing by this new exponent. So just remember, when we divide by a fraction, we really flip it and multiply. So instead of dividing by 3/2, I can multiply by 2/3. And 1 times 2/3 is 2/3. And then we still have our plus c. Finally, when we deal with something that's trig, we can't apply the power rule. The power rule works only when we have something like a variable raised to some power. So in this case, we use those trig formulas. We need to think the sine is the derivative of which of these original functions. So sine is what we're integrating, so we know it's going to turn into cosine. The problem is that this negative is not in our integral. So since it's not here, we can stick it on in the answer. And so in this case, sine turns into negative cosine, and then this 2 is just kind of hanging out. If, when you're done, you want to check your work, you can always differentiate your answer. So the derivative of cosine is negative sine. This -2 would drop down, and the derivative constant is 0. So then if we simplify, we get +2 sine x, which is what we started with in this problem. So we can always use that to check our answer. Okay. So we're going to look at a trinomial example. Again, we're just applying the power rule. It's reverse order and opposite operations as taking the derivative. So here we're going to add 1 to our exponent. And then this can kind of show us that new coefficient. It's 3 divided by that new exponent. So in this case, it's just 3/5. In the next term, we're going to add 1 to that exponent. So we get x to the 3rd. Again, this right here shows me I'm taking -5 divided by 3. So -5/3. And finally, out here we'll have x squared. There's a coefficient of 1. That turns into 1/2, 1 divided by 2. And then just don't forget we have plus c. Okay? And we're going to stop there for this video.